This is the first method I will present now. So I don't have the time to go into details in terms of climate modeling, but this is, so sorry, it's in French. I didn't find this the same for in English. I'm so sorry. Usually climate modeling, how does that work? First, you got observation, you measure temperature, precipitation, wind. Physicians, colleagues are able to put that in terms every linkage, or I mean, every linkage we are able to understand right now, I mean, so far, are able to capture that in terms of equations. So here an example of a modeling equation right here. A lot of equations that are put into small point grids that represent the atmosphere, the big ensemble of the atmosphere. It is separated, it is cut into small pieces of atmosphere, and in every piece of atmosphere, we resolve this equation. So using, well, codage information and large computer, really big, two big computers. And with that, we're able to reproduce the climate we know. I mean, we try to actually, maybe it's not that good, but we reproduce the climate and at least all the linkage and the relationships between the components of the climate. And we are able to get a simulation of the climate that we then compare to observations to see if the model is good. If the model is not good, we delete it or we improve it. And then it's a circle when you use modeling for lots of things in climate. The two major questions you can answer to using climate modeling is first, what can we expect for the future, the near-term future or the long-term future? Since we are able to calculate what is probable, we can extend the simulation we do for the historical period to the future. That's where we have scenario. And the second thing is that we can reproduce the current, the observed climate, well, try to, and see what happens when we just extract some component. If we extract the volcano, what is happening? If we extract the solar irradiance, what is happening? If we extract the human components with the human activities, what is happening? That's what we use to, that's one of the methods to attribute some events. So how does that work? On this graph, to illustrate how it works, I represent you the global, the change in global surface temperature. In black, you have the observations, right? You have well, not reconstructed, I think it's the real observed temperature, well, temperature change, so relative to an historical reference. So in black here, you have the observations of temperature changes. 0 means no changes, +1 means +1 degrees, etc., etc. In orange, shaded colors, orange colors, represent what the models are capable to simulate and to reproduce temperature. So the solid orange, dark orange line is here. And the shaded area around are the uncertainties. We are able to say at 95% confidence that the temperature evolved in that range of temperature, but there is uncertainties, obviously. And the mean, the multimodal mean or multimodal median right here is represented by the solid orange line here. So with all we know about the climate, so natural forcings, human components, we perform the same simulations, but extracting the human activities, so all the human anthropogenical greenhouse gases emissions. So only keeping natural forcing, so mostly solar radiation and volcanic radiation. And we obtain the green line right here at the bottom of the graph. The difference between the two gives us an information about the attribution. If there is a difference, if the difference is positive, so if when we compare the factual, so in orange, to the counterfactual, the green, if the difference is positive, it means that it's warmer in our current climate. If the difference would be negative. So picturing that the orange graph will be below 0 right here, it would mean that the current world, and due to global to human activities, the climate is cooling and is colder than without any human influence. That's the first way to try to attribute a trend or a specific event. For example, in the graph, let's say we have a year with a very, for a specific location, for example, in Togo, we have a year with a very strong, very warm temperature, very hot temperature. We can try to attribute using climate modeling if such warm year would have occurred without any global warming, without any human emissions. And to go a little bit deeper here, just quickly, currently I'm working with colleagues to try to study the impacts and the attribution of excessive rainfall and drought on maize yields in small input systems in Africa. What we do is that we use factual and counterfactual simulations of climate. Then we perform simulations of crops, so maize crops, using both this factual and this counterfactual climate. And we compare the two of them for 5 sites in Africa, so 4 sites in West Africa and 2 sites in, well, extended East Africa. And we compare what are the yields. We are trying right now, it's very an ongoing project. We are trying to compare if there is an attribution, there is a significant difference between factual yields and counterfactual yields, and more importantly, so due to extreme climates, and more importantly, in system when you don't add that much fertilizer, is the global warming, what is the impact of the global warming, how adding fertilizer can adapt crop yields to counteract, let's say, global warming effects. So this is the kind of attribution studies in terms of impacts on agriculture we are currently conducting, and we hope to provide some results by the end of the summer, but well, a lot of things to do, obviously. So this is the first type of method, dynamical modeling. You model a world without, you dynamical model a world without human and a world with human, and you try to understand the climate interactions. Another way is also a less intuitive way, but a more accessible way for users to conduct analysis. In this specific statistical modeling method, you don't have to know how a model works, and you don't have to run a model, a very huge dynamical model that takes time, that is big in terms of computing resources. So how does it work? We have to use some distribution rules. So for those of you today who are familiar with coding, so using R or Python or whatever, there is functions that do the work for us. I'm not a statistician for you, just for you to know. What we do in terms of attributions when we use the statistical models is similar to the dynamical one. We want to compare a world without a world with global warming and a world without global warming, and try to attribute an event or a trend. But in this case, we are only going to use observations, so only the world with the global warming. And what we do is that we're going to detrend, we're going to not simulate, but model the behavior of the temperature without global warming, but only using statistics. To do so, usually for attribution studies, we use what is called the generalized extreme value theory, the GEV. And what we do is that when we have, let's say, a time series of data, for example, you have, I don't know, the annual maximum temperature for 40 or 50 years for a given specific locations. We are going to calculate a model that reproduce the distribution of this specific metric. So here, the annual maximum temperature. This is going to create a line, a function that gives us the behavior, the mean behavior, the statistical behavior of the evolution of maximum temperature for a given location. Then this particular distribution, model you've created. So, for example, here is an illustration. It's not a real data. It's not real. It's just an illustration. Let's say I have a distribution of data, so maximum annual temperatures that are my dots right here. And the GEV model was created, so using a different parameter, statistical parameter. Once again, the code and the functions to do it for you. But if you are interested, I will give you paper with the right equation of that. The model is created and corresponds to the black line at the center. So it's not the same exactly because it's a model, but it's pretty much accurate. And then we are going to, once we have this GAV model for a given data set, we are going to test how this GAV model evolves, scaled to global mean temperature or CO2 concentration. In other way, how the mean temperature, global mean temperature can statistically explain how the GEV model creates from the observation dataset can evolve. You explore how the GEV model evolve depending on this original, let's say, that input dataset. So it's statistics, but once again, it's even if you're not a statistician, which I'm not, once again, it's really common to use this approach, at least to have a rapid overview of a given indicator. For example, you have a flood somewhere in 2022. You are going to define an indicator that can provide you the information of a flood, for example, a heavy rainfall indicator, an annual heavy rainfall indicator, over a large period of time. And then you specifically assess how this 2022 indicator behave depending on its place. Well, let's say how the specific 2022 indicator behave all over the time series that itself evolves along the global mean surface temperature. Yep, so I will provide an example to make myself, hope, more clear here. When you conduct the statistical attribution method, you want, once again, to assess the probability of a given event. For example, there has been a strong fire in Cape Town in South Africa in 2021 in April. One can ask, is this fire attributable to global warming? So the increase of global mean temperature. Using the GAV model, the GAV modeling statistical model, we are able to, so first you select an indicator. So one indicator for fire assessment is a fire weather index, FWY. So you have an annual or an April or spring one indicator per year, and you try to, in observations or in models or in all of this combined, you have a time series of this given indicator, and what you want to know is if this particular value in 2021 is related, it can be caused, statistically speaking, by the evolution of temperature. So using your GAV statistical method, you fit this evolution of the fire index over the global mean surface temperature, and then you analyze how it can be, how it evolves. You analyze it how it evolves in the current climate. So here it's represented by the red lines, and I'm going to detail this figure just right after. And you explore the same models in a detrended world. So using the same GAV model, but you detrend it by 1, 2, 3 degrees, whether you want to explore it, how you want to compare it to a colder world or warmer world, and you compare the two DAV models, the two lines, the red and the blue lines. So let's be more specific here. Here you have what is called a Gumbel plot. So it's a return level plot. It means that you have on the y-axis, you have the value of a given indicator. For this example, it's the value of the fire index. The x-axis are the return time, the return year of a given value. It means that depending on the model you have, the datasets that are providing a model using GAV, for a specific value of, I don't know, 60 here, you look at the red, let's say the red curve, a fire weather index of 60 has a return period of 4 to 5 years. So statistically speaking, you will have a value of 60, I can't remember the unit, but this specific 60 fire index, fire weather index every 4 or 5 years, statistically speaking. If you want to attribute a specific event, so in this example, 2021, the 2021 event corresponds to this value of the fire weather index, so 67.16, right here, and illustrated by the purple line right here. The red line is the model, the GAV modeled distribution of the fire weather index. It's a model that simulates how the fire weather index behave along with global mean temperature. The blue line is the same, but detrended, so with the temperature colder by minus 0.2 degrees than currently, so more or less what we call the pre-industrial world, so without any effect of global warming. Okay? What we can compare is the return time of both of these 2021 events, but in both climates. To do so, you read the return time, so the x-axis here. You read on the x-axis when you cross your model, so first the red one, with your event, so the purple line right here. For the current world, so for the red curve, so in the current world climate, you have a return period of this 2021 event right here, 9 years. It means that currently, so with the global warming, you have a return period of such 2021 fire of every 9 years. The same for the detrended world, so a world without global warming influence, or at least without current warming. You read the return period pressing the blue curve and your event curve right here. And we are about to 20, I don't remember, I think it's 2022 a year. So currently with the global warming, in this example, you have a return period of the event of every 9 years, statistically. And without global warming and human influence, statistically, we will have a return period of such event of 20 years. So more than 2.2 less probable event without any global warming. So that's how it's done. For any particular time series, for any particular, if you do have a time series of a variable that are relevant for you, here it's a time series for the fire weather index, and we want to acknowledge, we want to assess how the fire in 2021 can be attributable to the evolution, to the increase of temperature. In this particular event, we can say that due to global warming, the event in 2021 was 2.2 more probable because of global warming. In a world without global warming, we would have 2.2 less more probable, we will have 10.2 less fire event in Cape Town in South Africa. There is a specific website that is also providing impacts and climate data that is called Climate Explorer. You have the link here. Once again, I will provide it. So it's also it also provides data sets, as I present in the first part. But in this case, it's also provide tools and methods to attribute some time series. So I'm unfortunately don't have that much time, I think, to go into details. But I would be glad to detail it by mail or later or anyway. But on this specific website, so Climate Explorer, you can download your own data set. Let's say you have data sets per year, you have a time series per year of crop yields in a specific location on your region of interest. You can upload it yourself, so it's freely accessible. You just have to register with an email address. You can upload your own data on this specific website. It will quickly plot some results, some information in terms of distribution, in terms of evolution, in terms of statistics. And also, you can explore how it can be attributable to global warming. You have a box, you have a window that's called trends in return times of extremes. You have to select some specific information. I have to pass it really right away, but I would be glad to explain it better with you. And you obtain values. Not all of them are interesting. Only the return period, as I explained before, the return period in a colder world and the return period in the current with global warming world right here, and the ratio between the two of them. If the ratio is way more superior to 1, it means that there is an attribution. If the ratio is below 1, way more below 1, there is an attribution. Well, in another case, it means that it would have been more probable without global warming. So only to conclude fast, I'm sorry, I have to, if we want to discuss, I really need to go fast here. Just to quickly conclude, Africa is already impacted by global warming, and it's both visible in climate historical observation, in situ observation, satellite-based information, and also using climate simulations and impact simulation. It's the case in agriculture, but not only, there is also sectors that are adversely affected. There is a lot of web platform that has been used, and some of them provide more friendly and easier accessible access to such data and visualization. So you don't have to read the IPCCs, all of the references. You don't have to plot everything by yourself. You don't have to download all the data by yourself. More importantly, one platform I had the chance to contribute to, which really provides friendly user information. And attribution is a complex research field that is really important to try to provide information about the responsibility and the causality, the cause of some events like fire, food crises, floods, heat waves, fires, wildfires. Many methods exist actually. I just talked about dynamical modeling, statistical modeling. Both can be also combined to provide an even more robust attribution results. And in both cases, we compare factual and counterfactual climates. These are keywords in terms of attribution. And yeah, I will finish here if we want to discuss. And please feel free to ask me your question about attribution or about prior impacts section. Thank you very much.